This problem has us find the maximum force P that we can apply to this system before motion is going to occur. So we are trying to find what I will call P max before motion. And we have these three bars, and we are given some information about their coefficients of static friction, which I'll copy down here. Mu AD is going to be 0.2, mu BA 0.3, and mu CB is 0.5. Okay, so we are looking for how hard we can pull this just before there's going to be some sort of motion in the system. And looking ahead, there's going to be more than one possible way that this system could move. So we're looking for really the minimum force it's going to require to start the movement, which is to say it's the maximum force we can apply before there would be motion. So there's friction between all of our surfaces here. So this is going to be like a frames machines type of problem where we're going to need to model the interface between the different surfaces that are capable of moving relative to each other. So we're going to have a free body diagram for each individual member. The bar A, B, and C will each get its own picture. And I'll give it all the same coordinate system here, x right and y up. So I'm going to start with what I think will be the easiest one to begin is bar A, because an added thing we have to look at with these free body diagrams is when we're looking at the friction, when we're looking at the normal forces, we're going to have to think about ahead of time, which way do we think each of these bars is going to want to move relative to the surfaces it's touching. And as we'll see when we start to model A. So A I like to start with in this one because our applied force is directly touching A. And we'll see how it links to bar B and then bar C. And so we have A sitting here. And we need all the moments, all of the forces that are acting on A. Now, one thing to look at here, we are not given any dimensions in this. We don't know the height, we don't know the length. If we don't know length dimensions, we're not going to be able to look at or consider tipping. So that's going to come into play when we start modeling the forces that act on this and where those forces are located. So I'll start with just the applied force P first. I don't know its value. That's ultimately what we need to find. So that's a good place to start. Other forces that act on the bar is going to be the weight of the bar. Now we're also not told anything about, is it a homogeneous bar, which again is not too important in this one because we don't even know its size dimensions. So for this one, we're not going to be able to consider tipping. So I'm just going to put the weight pointing down. Horizontally, it's going to turn out not to matter because we're not going to use any moment equations because we're not considering tipping. So if the weight is down, it is not falling through the floor because there's going to be the normal force of the floor pushing up at D. So I will call this NAD for the normal force between block A and the ground D. And notice it must be pushing up on this block. And we still have some other forces to contend with. We have block A or bar A in contact with bar B, and they are not rigidly attached. However, they are in contact with each other. So because they're in contact with each other, we're definitely going to have a contact or a normal force between them. And this is kind of less obvious, I think, that we have to include this, but there is going to be a force down. That's the normal force between A and B. So there's going to be this NAB acting, or NBA. I'll actually rename all of these to be in alphabetical order just so everything is consistent and we're not missing anything. All right? And also because bar A and B are not rigidly attached and there is some roughness between them, it's not a smooth surface between A and B, there's friction, there's going to be a friction force. And friction forces are always going to be parallel to the contacting surfaces where the normal force is always perpendicular, as we just saw with NAB. It's a horizontal surface, NAB is vertical. It's a horizontal surface, so the friction force is also horizontal. But here we have to think about what direction should it point. So on a body, the friction force is always going to point in opposition to either the motion or, in this case, the impending motion. Which way in the absence of friction would this bar want to slide? So that's why starting with bar A I think is the easiest one, because if we're pulling with that force P to the right, then it would seem the bar would want to travel to the right. Therefore, the friction force is going to oppose the motion it wants to achieve. So there's going to be this FAB force between surfaces A and B that is preventing that motion. We also have to consider that the floor D, or the ground D, and this bar are also in contact, and that too is not smooth. So actually what we have here is another friction force between the bar and the ground, and that's going to be called FAD. So bar A has the top surface and the bottom surface in contact with other surfaces that are not smooth, so there's a normal force between each of those surfaces and this frictional force. And both of them point to the left because, again, those surfaces, we think that bar A wants to slide to the right relative to both of those surfaces it's in contact with. So now we have all of the forces that are acting on the bar at A. There's two friction forces. The normal forces must be pushing on our object. So if we look at that free body diagram, we have two normal forces, we have two friction forces, and we have that applied force P. So I'm not going to try at the moment to write any equations yet. I'm going to keep going with more free body diagrams so we can see how this system all fits together. All right, so picture 2 is going to be of bar B. So let's see what forces are acting on this. Well, it has its own weight force, and that is 40 pounds down. And now it's going to have all of its reactions with the surfaces that it is in contact with. At the bottom, bar A, and at the top, bar C. So two of these are already going to be figured out. We drew NAB down in the first picture, so that normal force must be up in this picture. So this is the force that bar A is exerting on bar B that is preventing it from falling through the floor, or really traveling vertically. So it's the same force, equal and opposite in these two pictures that it appears in. And the same idea is going to be true with the friction force, FAB, because we think, and this is why starting with A was a good idea, FAB in the first picture pointed to the left because we think that bar A would want to slide to the right relative to bar B. So therefore, FAB must be to the left. It will be equal and opposite in this picture pointing to the right because we think relative to bar A, bar B would slide to the left. Again, this is relative motion. B could be completely still, and A moving to the right means that B is relatively moving to the left. Hence why FAB points to the right here. Now we're going to verify all of these assumptions by making sure that all of our friction forces are positive and all of our normal forces are positive. But in these two pictures, it must be equal and opposite. So that takes care of the interface between bar A and bar B. Now on the top, it's between bar B and bar C. Well, bar C is going to be exerting a contact or a normal force on bar B. So we're going to have an NBC. And then we have the friction force between them. So again, we want to think of the relative motion. Probably, if we're pulling with that force P, bar A and B possibly want to stick together and slide to the right, which means that B wants to move to the right relative of C. So on this surface, because B we think wants to move to the right relative to C, the friction force is going to oppose that and point to the left. So on bar 2, we actually have one friction force to the right from A on B and one to the left from B on C. And looking at this picture, we have again 4 unknowns and we introduced 2 more unknowns. So I'll do my final free body diagram here of bar C. Okay, so bar C will have its own weight, and bar C we are told weighs 60 pounds. So we need to include that. Here it's attached to that rope, with some tension in it I will call T. I don't know what it is yet, but I do know the direction of it is going to be along this 8, 15, 17 triangle. And what other forces are going to act on this? There's that contact force between B and C, or that normal force. Well, we already know it must be equal and opposite as it was in the other picture. So this is the force that B pushes back up on C with, so that C does not fall down. So that is also this NBC. We have FBC in picture 2 to the left, so FBC must be in the opposite direction in this picture. And again, we think bar C would want to move to the left relative to bar B, therefore FBC must point in the opposite direction, which would be to the right. And that is actually everything acting on bar C. The normal force pushing up on it, its weight force down, the opposite direction of friction force, and now this tension that connects it to the wall at that specified angle. So free body diagrams, we have 3 of them, and we see we have a lot of unknowns here. Before we start writing any equations, we're going to have 1, 2, 3, 4, 5, 6, 7, 8 unknowns happening from our free body diagrams, which means to solve this system, we're going to need 8 equations at least. Now, again, looking forward, free body diagrams, each one of these is technically a rigid body. However, we don't know anything about the dimensions, the lengths or the heights. So we're not actually going to be able to write any moment equations out of these free body diagrams because we don't know how long any moment arms are. But we're not going to be considering tipping, so that's not going to be a big deal. But what that's going to mean is actually only 2 equations out of each free body diagram will be possible. So free body diagrams are actually only going to give us 6 unknowns. So we can start looking at what those equations are. We'll get 6 of them, presumably, but we're going to need some extra equations, and we'll see what that looks like. I'm actually going to start with free body diagram 3 for my first equation, because it has the fewest unknowns. If I sum forces in the y direction in 3, I am going to get a negative 8 over 17 times the tension, plus NBC, in this picture it points up, minus 60, the weight of this bar C. And equation 2, I'll stick with this picture and sum forces in the x direction in picture 3. These are 0. In the x direction, I'll have minus 15/17 times t. And in this picture, FBC points to the right. And yeah, again, cannot get a moment equation here. So I'll move on and start writing more equations. Nothing yet is solvable. I have 2 equations, but 3 unknowns. If I look at picture 2, let's go y direction first. It's an equilibrium, so I know it's equal to 0. I'll have negative 40 from the weight, minus NBC pointing down in the negative y direction, plus NAB pointing up. And then the x direction, I'll have here minus FBC plus FAB. And moving on to the last free body diagram 1, I'll do the y direction first. I have its weight force down, minus 20. I have now NAB pointing down. I have NAD pointing up. And the x direction, I have negative FAB in this picture, minus FAD plus P. Those are all of the equilibrium equations that we can get for this because the moment equations don't show up, or we can't use them. We don't know the dimensions. We have 6 equilibrium equations. Again, we already counted, we have 8 unknowns, so we need more equations to be able to solve this. Because we are Presuming we're in equilibrium or we're testing what would just take us out of equilibrium, these 6 equations are going to be true when we're in equilibrium. But now we have to think about the pending motion, the impending motion in this problem. So we have to think about the different ways that we could have motion in the system. Now, we kind of already thought about these when drawing the free body diagrams, but let's see, because we're not considering tipping, we're just considering slipping, 2 different scenarios could occur. So we could pull on that bar A, and it could slide out between the ground and B. So bar A slips out, B does not move, it remains attached to C, and A just slips out between B and the ground. So that would be what I will call scenario A. Another possibility, an alternative possibility, is that actually A and B stick together, and the 2 of them stuck together are going to slide out relative to the bar at C and the ground at D. So A and B stick together and slide together out. Now in this one, because C is attached to the wall by that cable, we don't have the scenario where A, B, and C stick together. C cannot move to the right. C has to stay stationary. So there's 2 possible movement scenarios. So scenario A is where A slips on, I'll say, D and B. So it slips out. B and C are going to stick together. So this is going to add new equations or additional equations here. So what's it going to take for A to slip relative to the ground and B? And when I say it's slipping on D and B, I'm really saying it is on the verge of slipping. So what is the force P that would just cause it to begin to slip relative to the ground and B? So here it has to slip relative to 2 surfaces it's in contact with at the same time, or be on the verge of slipping at the same time. So what has to occur is that both of the friction forces at those surfaces have to be at their maximum value. So that means that FAD, in order for this to just be on the verge of slipping relative to the ground, this must be at its maximum. And I can say here, FAD is equal to mu AD times NAD. That has to be true. They are equal when they are just about to slide relative to each other. And also, because it's sliding out from bar B, simultaneously it has to be true that FAB is at its maximum, mu AB, NAB. I cannot say anything about FBC because it's going to be, well, in this scenario, it should be less than its maximum, and that's something we can test. But there's other ways we're going to be able to test what's happening here as well. So that we had 7a and 8a, and if we look at our equations, we now have 8 equations, and we have 8 unknowns. So this set of the 6 equilibrium equations and these equations 7a and 8a for this scenario give us what should be a solvable system for scenario A. But let me develop also scenario B here so that we can then do the solve step all at once. We could solve this and then come back, but the alternative are that A and B are stuck together and they slip or on the verge of slipping on D and C. So in this scenario, that equation 7a and 8a do not apply. We have a different equation 7. And here, actually, equation 7b turns out to be the same. This must be true in this scenario as well. It still has to be true that FAD is at its maximum value because still that bottom block has to slip relative to the ground. So 7b and 7a turn out to be the same. But 8b, that's different. If blocks A and B are stuck together and they are sliding relative to bar C, now it is FBC that must be at its maximum. So we can set it to its maximum, and now equation 8b makes this true. Mu BC times NBC is equal to FBC. And in this situation, we are not imposing anything on FAB, just on BC and AD. So we have 2 sets of 8 equations to test our 2 different scenarios. So we want to see which one of these is the one that is going to happen. So in our solve step, and now there's a lot of equations here, there's a lot of, nothing is really simple to solve. I'm going to solve this in Mathematica. So I want to solve scenario A, and then I'm going to solve scenario B, and then I'm going to see which is the one that is actually going to happen first, with the least amount of force. So which impending motion scenario would happen if we applied that minimum amount, or really the maximum amount of force before we have motion. All right, so let's look at how we can solve this in Mathematica. Since we have 8 equations that we have to solve, 2 sets of 8 equations actually, we don't really want to do this by hand. Let's use Mathematica. So I'll put in my equilibrium equations first. I'll call it ECHEC for equilibrium equations. So let's see, the first one, I have 0 equals negative 8 over 17 times t plus NBC minus 60. Notice here I am using lowercase for everything that I am defining, because Mathematica uses uppercase for its reserved or built-in functions and variables, and lowercase are for us to use to build our own. Equation 2, negative 15/17 t plus FBC. So I'm just going to make this list of 6 because these equations are going to be true for both scenarios, because we are in both cases presuming, or we're under the premise of static equilibrium, because we are not looking at a dynamic system. We're seeing if we're in static equilibrium, which of these scenarios is on the verge of having movement first. In equation 4, negative FBC plus FAB. Equation 5, negative 20 minus NAB and plus NAD. And equation 6, negative FAB minus FAD plus P. Okay, so those 6 equations are entered in, and I'll suppress it with that semicolon, and I will run it. So now it's saved that list of 6 into EQ. So let's look at scenario A. We're going to add 2 more equations. So I'll make that list. I'll call it EQA. And in this set, FAD is at its maximum of mu AD times NAD. I'll just put in the number here. Mu AD was 0.2 times NAD. And also it's going to be true. Let me just format this the same way. It's also true that FAB is at its maximum, mu AB, which was 0.3 times NAB. And I'll put in, while I'm entering equations, let's put in the scenario B equations, which actually the first one is also true in scenario B. But the second equation, the 8th equation overall, is different. FBC is equal to mu BC. Check on that again. Mu BC was 0.5 times NBC. So with all of my equations down, now I can go about solving them. So solve, capital S, because it's a built-in function in Mathematica. And then I have, the way I define EQ, and then EQA, EQB were as lists of lists. So one way I can do this is I can take the union of my lists and put them together. So if I just run, let me just run this by itself first so we can see what it looks like. What union does, just like with any other set, it takes all of the elements and puts them in a single list. So that's what Mathematica wants when we are going to call that solve command. So this is what it's going to solve. And for a linear system like this, since we have the same number of equations as unknowns, Mathematica is going to know that we want to solve for the 8 unknowns based on the 8 equations. There's other ways to use solve, where we can specify the variables to solve for, but this one we just want to solve for everything. All right, so this is what we get. Let me make this a little bit nicer to look at here. I'm using this set precision around my answer, which is going to be, what I'm telling it is only show me 3 significant figures instead of this long list of them. So it's the same answer I had before. It just automatically is rounding it to 3 significant digits, since that's all I really care about for this. Okay, so now we see we have our list here of all 8 of our unknowns solved for. This is under scenario A. And we can see we have our FABs, FAD, FBC. So one thing we can check right away is all of our frictional forces are positive. That's crucial. And all of the normal forces are positive as well. That has to be true in these friction problems. Friction forces must be positive, normal forces must be positive. Now we find that this would happen with an applied force of 63.5 pounds is when scenario A would take place. Now, we could check and make sure that FAB was not, or FAD was not too high, or FBC was not too high. Or alternatively, let's look at what happens if we solve the second set. So the only difference is I still want to use my equilibrium equations, but now I want to solve them with 7b and 8b instead. So I'm solving a different set of 8 equations, and I want to see what that answer looks like. So solving those 8 equations, 1 through 6, 7b, 8b, we get FAB, FAD, FBC are all positive, so that's a good sign. NAB, NAD, NBC are all positive, so that's also good. We get a larger value for P, and we get a larger tension. The tension doesn't matter too much. So different ways we can conclude what our answer is. We can look at those 2 P values first. So we see that in scenario A would happen with an applied force of 63.5 pounds, and scenario B would happen with a higher force, 69.3. So we want to take the lower actually of the 2 because scenario A would happen first if we were, let's pretend we are slowly increasing that load P. Scenario A, that the bottom bar is going to slip relative to bar B in the ground is going to happen first. And it's already going to be in motion before scenario B could happen. Another thing we could look at is why is scenario B not the answer? Well, we can look at the friction forces and see are they all feasible. Well, we already enforced that FAD was at its maximum, FBC was at its maximum, but what is happening under this scenario to the other friction force, the FAB, which is 40.9. So we want to check here, is that above or below the maximum allowable? So 40.9, is that less than, mu AB, which was 0.3 times NAB. In this scenario, that normal force came out to 122. And we come out with false. Well, let's see what that actually is. 0.3 times 122. So in order to have equilibrium in scenario B, FAB would have to be 40.9 pounds. However, the maximum it can be is mu times the normal force. So mu AB times NAB. So testing 0.3 times 122 is only 36.6. To maintain static equilibrium requires more frictional force than is possible, more static friction force than is possible for FAB. So for that reason as well, we can conclude that scenario B is not the one that happens. But let's go back and just write it down and discuss from there. Recapping just the final results here from scenario A, this came out with a P of 63.5 pounds. So I'll call it PA. And in scenario B, we got a P value of 69.3 pounds. So for the reasons we discussed, one, we're really looking for what is the lowest P before motion occurs, and that will be P max. That means that scenario B is not the answer. Again, it has a higher weight force or a higher applied force, which we saw, and it violates static equilibrium in that it would require FAB to be too large, larger than it possibly could be. So what this tells us is that the maximum P is the minimum of these 2 P's, 63.5 pounds. So that is the maximum force we can apply before motion would occur in this system.